Hello, this is Dr. Hanaa Assil, and this is Unit 6 of June 2020 in the Pearson Edexcel International A-Level Chemistry. So let's take a look at the questions. The first question says compound A is a green solid containing one cation and one anion. So, as a beginning, we should know that several transition metal ions could give a green color, and also we could have a mixture of something that's blue and something that's yellow that would give a green color. So the question goes on and says a sample of compound A was dissolved in distilled water forming a green solution. Aqueous sodium hydroxide was added to the solution of A until there was no further change, and we got a pale blue precipitate and a yellow solution were formed. The pale blue precipitate, which we're naming B, was separated and tested. B dissolved in excess ammonia to form a deep blue solution. So, if we add sodium hydroxide, it gives a pale blue precipitate, and adding ammonia gives a deep blue solution. That's obviously copper 2+. Copper 2+ in solution is blue. When we have the copper complex with 6 water ligands, this is a blue solution. Now we're adding a little bit of ammonia or a little bit of sodium hydroxide, it gives a blue precipitate. When we add excess ammonia, then we have a complex of copper with ammonia and water. So B, precipitate B, is the copper hydroxide, or we could refer to it as a complex between copper and 2 hydroxides and 4 water. Now, we are told that B dissolved in excess ammonia to form a deep blue solution containing the complex ion D. Well, we should know that D should be the complex between copper, 4 ammonia, and 2 water. Again, please note the overall charges. Copper alone is a 2+ ion. If it has 2 hydroxides, then there is no overall charge. But if it is complex to ammonia and water, then we have the overall 2+ of the copper. When another portion of B was heated gently, the solid turned black. We already decided that B is copper hydroxide. When we heat it, it does turn black because it will form copper 2 oxide. Excess concentrated hydrochloric acid was added to a further portion of B. We already know that B is the copper-water complex. We're going to add concentrated hydrochloric acid. We end up with the yellow solution containing the copper complex with 4 chloride ions. So identify by name or formula the complex ion that forms in the yellow solution. That is the copper with 4 chlorides. Remember, each chloride has one negative charge. So with the copper 2+, we have an overall of 2-. The yellow solution C was tested. So we already had, at the beginning, we said the solution was green because we had something blue and something yellow. So now we're talking about the yellow one. 5 cm³ of dilute sulfuric acid was added to the same volume of C, and the mixture turned orange. Now, yellow, we added acid to it, it became orange, and then when we add 1 cm³ of ethanol to the orange mixture, heat gently, the mixture turned green. That should tell you that what we're starting with as a yellow solution is the chromate ion. Chromate ions, when you add acid, it becomes dichromate, and dichromate is an oxidizing agent. So if we add ethanol to the dichromate, the ethanol becomes oxidized and the dichromate becomes chromium 3+ complex. So that means that the yellow color of solution C is due to the chromate ion. When we add acid, it became dichromate, Cr2O7 2-, and when we used it as an oxidizing agent, it became oxidized to the chromium 3+ complex with 6 water ligands. So just the name or formula of the organic product formed, we said we added ethanol to what we now have decided is the dichromate. So we said if we add dichromate to ethanol, the ethanol is oxidized and my product is ethanol. Remember that oxidation of ethanol. If the product is distilled off directly, then what I have is ethanol, an aldehyde. And if we continue to heat it under reflux, it will end up becoming ethanoic acid. So either of them could be correct. While the dichromate itself now changes to chromate ion complex. Give the name or formula of compound A. What was compound A? That was the green solid that had 1 cation and 1 anion. We had already decided that the cation is copper 2+ and the anion is chromate, so the compound is copper 2 chromate. Give a possible reason why compound A is green. We said it's green because the blue color and the yellow color together are seen as green. This question is about 3 organic compounds, P, Q, and R. These compounds are isomers with the molecular formula C4H8O2, so all 3 of them have 4 carbons each. Compound P is a colorless liquid with a sweet, fruity smell. Of course, as soon as we are told that something has a fruity smell, that means that compound is an ester. Now, when a sample of P was heated with sodium hydroxide, a volatile product was formed. Remember that if you heat an ester with a base, it is hydrolyzed. It is broken up into the acid part and the alcohol part. The volatile product would be the alcohol. So a volatile product was formed which had a molecular ion peak in its mass spectrum at M/Z46. That means that the alcohol part is something with an M/Z46, and that means that is ethanol. The mass spectrum of P has a strong peak at M/Z43. M/Z43, that's the other part of the ester, which is the part that has the carbonyl group. So that tells us that our ester is ethyl ethanoate. When sodium hydrogen carbonate solution is added to separate samples of Q and R, effervescence occurs and a gas is evolved which turns lime water milky. Of course, if I have a substance and we add it to sodium hydrogen carbonate and it gives out a gas that turns lime water milky, obviously these are carboxylic acids. So both Q and R are carboxylic acids because they give carbon dioxide gas when added to hydrogen carbonates. Now we are told to reduce 2 possible structures of Q and R. We know that Q and R have 4 carbons, so we're talking about a carboxylic acid that has 4 carbons. What would be the possible structure? either we have a straight chain carboxylic acid with 4 carbons, so that's butanoic acid, or a branched chain in which we have a methyl group at carbon number 2, so this is 2-methyl propanoic acid. A simplified high-resolution proton NMR of Q is shown, and we are told to deduce the structure of Q. We already know that it is one of these. Fully justify your answer by referring to the number of peaks, the relative peak areas, and the splitting patterns in the proton NMR spectrum. So, which one of these is Q? Well, if we look at the straight chain butanoic acid, Q would give 4 peaks in the proton NMR, while the NMR that we have in front of us has only 3 different proton environments. So it must be the branched chain one, in which both methyl groups are equivalent, so there are a total of 6 protons, and they have on the neighboring carbon, so these are the ones that I labeled A, and on their neighboring carbon there is 1 proton, so these 6 protons are a doublet, so that is the A. B is the proton on the neighboring carbon, and of course that has 2 methyl groups next to it, so that's a septet. And the proton of the OH is always a singlet, and that means that is my structure. So the straight chain acid would give 4 peaks, so that's wrong. Q is the branched chain, so that is the one we're going to call 2-methyl propanoic acid. It has 3 proton environments, so that's correct according to the proton NMR spectrum. The 2 methyl groups give the doublet for 6 protons. The proton on the neighboring carbon is a septet due to 1 hydrogen, and the hydrogen of the OH is the singlet at about 11.9 ppm. Question 3 says, a group of students carried out an experiment to determine the rate equation for the reaction between bromide and bromate ions in acid conditions. The equation for this reaction is this, and we are given the procedure. So measure 10 centimeter cubed of aqueous phenol solution into a boiling tube. Add 5 drops of the indicator, methyl red. The mixture turns yellow. Add 5 centimeter cubed of potassium bromide, 10 centimeter cubed of acid to the boiling tube. The mixture turns red. Measure 15 centimeter cubed of potassium bromate into a second boiling tube, and then mix the contents and start a timer. Record the time when the color of the methyl red is bleached due to the presence of excess bromine. Repeat the experiment using different volumes of aqueous potassium bromate, adding distilled water so that the total volume of the reacting solution is always the same. And the first question is, 2 of the hazard warning signs for phenol are this. State the most important hazard associated with phenol in this experiment and the precaution you would take to reduce the risk apart from wearing safety goggles and the laboratory coat. So if we have this on phenol, and you should know that phenol is actually a liquid. So what do these hazard labels mean? Well, they mean that phenol is toxic and corrosive. What kind of precaution should you take? Well, this is not a gas, so please don't say in a fume cup. This is not a gas, it's a liquid. So if it is toxic or corrosive, we need to wear gloves since the phenol is corrosive, or you could say it could be toxic if it is absorbed through the skin. In both cases, you just need to wear gloves. Explain the purpose of the phenol in this experiment. What did they say? They said we put the phenol on the methyl red and then the potassium bromide and sulfuric acid into the boiling tube, and then the potassium bromate in a second boiling tube, and then we join. We mix them together. And this was the equation, and we're recording the time when the color of the methyl red is bleached from excess bromine. And that means the phenol, remember that if I have bromine in the mixture, phenol reacts with bromine. So at the beginning, bromine is being formed. As it is being formed, it will react with the phenol. But then at some point, all the phenol is used up, and that is when the indicator bleaches, indicating that all the bromine or the bromine is present as excess and all the phenol has been used up. So this is just to have a color change after a specific time or after a specific amount of reaction. We don't want the indicator to be bleached immediately. As soon as any bromine is formed, it would be bleached. But if we have phenol, then the phenol reacts with bromine, and then when that amount of phenol has been used up, any more bromine will cause the indicator to bleach. So just a way of making the disappearance of the methyl red color easier to see. How can we make the color change easier to see? If we use a white tile or a white paper. A student's results are shown. State why the total volume has to be kept constant. Remember, what we're measuring here is volume, but actually we're supposed to be comparing to concentration. We're supposed to have rate versus concentration. But if the total volume is always the same, then the volume is proportional to the concentration, and I can plot the graph with volumes instead of concentration. Plot a graph of reciprocal time, 1/time, against the volume of the bromate. So you need to label the graph paper, you need to, or the grid as they call it, and distribute the graduations, the readings equally. Plot the points with small x's, and then we join with a line of best fit. This should be a line that goes through the zero. State the order of the reaction. So if we're measuring rate versus concentration and it is directly proportional, of course this is a first order reaction with respect to bromate, since the rate is directly proportional to concentration. Now, reciprocal time, or 1/t, is used to measure as a measure of rate. So just the assumption on which this depends, refer in your answer to the shape of a typical graph of reactant concentration against time. Now, the typical graph of concentration versus time would be this. Concentration decreases with time. But if we are going to use this as a measure of the rate, what would be the assumption? The assumption is that the end point is within that region where the graph is going down straight, as if it is a tangent at a certain point. This is when the concentration versus time is linear. Another student accidentally measured 8.5 centimeter cubed of potassium bromate rather than 8 in run 4. In run 4, they were supposed to measure 8 centimeter cubed of bromate. Now this student measured 8.5 and put it into the mixture. Explain whether or not this portion should be discarded. Well, if we put 8.5, that means the point when plotted on the graph will be a little way off. Remember, if you look at the graph, there are points that are a bit above or a bit below the line. So if we make a mistake like this, then the point will just be somewhere around the line of best fit, and all we need to do is we should add water so that the whole volume is still the same. So instead of adding 7 centimeter cube of water, then we added 0.5 more of the bromate, then we need 0.5 less of the water so that all the overall concentration is still the same. All the volume measurements in this experiment were made using a 50 centimeter cubed burette. Give a reason why the potassium bromate solution is first measured into a separate boiling tube rather than pouring it from the burette or dropping it from the burette directly into the reaction mixture. Remember, when we add, as soon as the reactants mix, the reaction starts, and I should start the timer. But then using a burette, the burette is slow, so it will take some time to add the 50 centimeter cube. The reaction would have started already and the results would be inaccurate. So we're putting the 50 centimeter cube in a separate boiling tube, and then when we're ready, we mix the boiling tubes together and start the timer to make sure that the reaction does not start before all the bromate has been added. Since using a burette, the process is slow. Give 2 reasons why run 1 has the lowest uncertainty in the volume measurements. Where is run 1? Run 1 is the one where we have the largest volume, and you know that the larger the reading, the less the uncertainty. So the volume of the bromate is the largest, so we have the lowest uncertainty. And in that reaction mixture, we're not measuring any water, so we have 1 less measurement to measure, and that means there will be less uncertainty in the readings. State the changes that you would make to the procedure to obtain the data needed to determine the overall rate equation for the reaction between bromide and bromate. The table showed results when we change the concentrations of bromate, and that would give us the order with respect to bromate. But if I want the overall rate equation, then I need to know what is the order with respect to the other reactants. So I will need to repeat using the same concentration of bromate but different concentrations of bromide. Same concentration of bromate and bromide but different concentration of acid, and so on. And in every case we need to add water to keep the total volume constant. Question 4 says a group of students prepared aspirin from 2-hydroxybenzoic acid using ethanoic anhydride, and were given the equation and some data in a table. The procedure was weigh 2 grams of 2-hydroxybenzoic acid, put it in a pear-shaped flask, clamp the flask, suspend it in a water bath containing cold water, add 5 centimeter cube of ethanoic anhydride to the 2-hydroxybenzoic acid, add 5 drops of concentrated sulfuric acid to the mixture, add anti-bumping granules, fix a reflux, so we're heating all of this under reflux, warm the mixture by heating the water bath using a Bunsen burner, gently swirl the mixture until all the solid has dissolved, continue warming the mixture for another 10 minutes, remove the flask from the hot water bath, add 10 centimeter cube of crushed ice, some distilled water, stand the flask in a beaker of iced water until no more crystals form, and filter off the aspirin crystals using a Buchner funnel suction apparatus. Wash the aspirin crystals with a minimum volume of iced water and recrystallize the aspirin using a mixture of ethanol and water. Now, What is the question? Give a reason for placing the flask in cold water in step 1. When they put 2-hydroxybenzoic acid, they put it into cold water. This is because the reaction that is going to happen is exothermic, and we don't want it to become too hot, or we don't want the temperature to rise. So just the purpose of the concentrated sulfuric acid, of course we're putting concentrated sulfuric acid in this case as a catalyst. This is basically an esterification. Then the question says, show by calculation that the ethanoic anhydride is in excess in this preparation. So what do we have? We already know that we put 2 grams of 2-hydroxybenzoic acid, and then we added 5 centimeter cubed of ethanoic anhydride, and we are given information in the table that will allow us to get the number of moles of each. So let's say, for example, the ethanoic anhydride, we are given the volume, and in the table we're given the density. So I can get from density times volume, I get the mass. And then I can use that to get the number of moles of ethanoic anhydride, mass over molecular mass, which is also given in the table. And this is the number of moles. Now, the 2-hydroxybenzoic acid, we're given 2 grams of 2-hydroxybenzoic acid. I can use that to get the number of moles of the acid, mass over molecular mass, that is given. From the equation that was given at the beginning of the question, we can tell that the ratio of moles, I should have 1 mole of 2-hydroxybenzoic acid reacts with 1 mole of ethanoic anhydride. And that means the number of moles of both of them should be the same. Actually, the one for the ethanoic anhydride is much more than needed. So that means that the anhydride is in excess. One student drew a diagram of the apparatus used for reflux. Identify 3 errors in the student's diagram. What's wrong with this diagram? First of all, when we do heating under reflux, we don't use a conical flask. We use a pear-shaped flask, or we could use a normal round-bottomed flask, but not a conical flask. So a pear-shaped flask should be used instead of the conical flask. What else is wrong? The water should be going in from the bottom out at the top, not the other way around. What else? At the top here, he has a bung. The condenser is closed with a bung. This condenser should not be closed at the top. So just the purpose of adding crushed ice and distilled water in step 5. Step 5 says remove the flask from the hot water bath, add 10 centimeter cubed of crushed ice and some distilled water. Of course, this is to cool the mixture so that I can have crystals forming, and I want as much of the crystals to form, so we're cooling it even more with crushed ice. This means we get higher yield of aspirin. Filtration in step 7 is carried out under reduced pressure. Remember, we have 2 types of filtration. This filtration is the one that is under gravity, so this is the ordinary gravity filtration. But the Buchner funnel, this is the reduced pressure. So we're asked state 2 advantages of using a Buchner funnel under reduced pressure compared to using the normal filtration under gravity. Of course, the Buchner funnel, when we join it to a pump, that's the one on the right, this is a faster filtration. This is faster. If you've done any filtration using a normal funnel, you would know that this takes some time. And when we use the pump to pull the filtrate through, this helps to remove water from the crystals, and this helps to dry the crystals. Describe how the purity of the recrystallized aspirin could be tested. Remember, how do we test the purity of a solid? We determine the melting point, and it should melt sharply at the melting temperature that is indicated in the table. It says it should melt at 136. So if it is pure, it should melt sharply at 136. And that's the end of this paper. Thank you for listening. I hope this was useful, and good luck in your exams.